Good morning, sir. I am Manisha from CSC Department. Roll number 244G1A05 enter. Subject Physics. Topic name Schrödinger's time independent wave equation. Schrödinger's time independent wave equation. Introduction to Schrödinger's wave equation. Schrödinger's wave equation is a fundamental equation in quantum mechanics. It describes how the quantum state of a physical system changes over time. And historical background. Erwin Schrödinger formulated the wave equation in 1925 as a response to quantum theory challenges. This work built upon the ideas of wave-particle duality introduced by Louis de Broglie. The equation significantly advanced the understanding of quantum machines and atomic structure. The one-dimensional time-independent Schrödinger's equation can be written in the form h squared by 2m d squared psi by dx squared plus v psi equals to e psi. Here, h is the reduced Planck's constant and m is mass and v is the potential energy. The wave function pi contains all information about the quantum systems and then components of the equation. The potential energy varies based on the physical situation being modeled. The energy eigenvalue represents the total energy of the system and physical interpretation. The wave function pi provides a probability distribution for finding a particle in space. The square of the wave function's absolute value pi gives the likelihood of locating the particle. The equation illustrates the wave-like behavior of particles, again with quantum principles. Probably a quantum particle in an infinitely deep square well has a normalized wave function that is given by psi into x equals to root 2 by L sine pi L by L. And boundary conditions. Solving the time-independent Schrödinger's equation often requires specific boundary conditions. These conditions depend on the physical constraints of the system, such as potential wells or barriers. Proper boundary conditions ensure that the solutions are physically veiled and normalized. And the next is applications in quantum mechanics. Schrödinger's equation is crucial for analyzing quantum systems like electrons in atoms. It is used to derive energy levels and wave functions for various quantum states. The equation helps in understanding phenomena such as tunneling and quantum superposition. And the particle in a box problem. A common example is the particle in a box model, which simplifies the amplification of the equation. In this model, the potential is zero inside the box and infinite outside, creating boundary conditions. The solutions yield discrete energy levels and wave functions, illustrating quantification. Quantum harmonic oscillator. The quantum harmonic oscillator is another classic application of the time-independent wave equation. It describes system-like molecules vibrating around stable equilibrium positions. The energy levels are quantized, leading to equally spaced energy states. And next, limitations of the equation. The time-independent Schrödinger's equation assumes a time-invariant potential, which may not always hold. It does not count for certain relativistic effects, which are covered by more advanced theories. Additionally, it may not apply to systems with strong interactions or those requiring time-independent analysis. And the next is advanced topics. More complex systems often require numerical methods or approximates to solve the equation. Techniques such as theory and variational methods are commonly employed. Understanding these advanced topics depends insight into quantum machines and its application. Conclusion: Schrödinger's time-independent wave equation remains a cornerstone of quantum machines. It provides a framework for understanding the behavior of particles at the quantum level. Continued exploration of these equations leads to new discoveries in physics and technology. And thank you, Mr.